The reason I teach causal inference in this course is because, as I mentioned a little bit last time, when you do machine learning, it's just a black box that you get back if you do it in the particular way that I'm going to teach. So if you don't have parameters inspired by causal inference that don't rely on a model, right? Because this is model free. We're fitting things without making any particular assumptions on what the prediction function looks like or other aspects of the distribution. Then you just can't go to a coefficient. Like you can't easily derive a parameter that's sort of independent of the model. And so causal inference gives you, it's a very serious field, right? I mean, it's a field on its own. People study it to figure out whether you can identify certain causal effects from observational data. That's a big part of it. It also has been, it's been developing methods where you can put in a graph and say, I'm interested in a pathway, and then it'll say whether automatically will tell you you could identify this by the data or you couldn't. The data has information about that parameter versus not, so it can be, it's going towards a fair amount of automation eventually. And there's another branch of causal inference which really tries to construct the graph from the data. So you put some constraints on the data sharing distribution, and you have a bunch of variables, and it essentially operates on the correlation of them and trying to recreate the graph. Now, we're not going to, yeah.
Conceptually, in terms of the model kind of being a black box.
Yeah.
People also talk about other prediction models like random forest,
Mm-hmm.
also regression,
Mm-hmm.
extreme gradient boosting, and all those things.
Sure.
But I feel like and then they show an importance table where you kind of see a bar graph almost of these covariates.
Sure.
And then potentially that is a regression model. So that doesn't seem like a black box to me, right? Because you can say these are the 20 covariates that were ultimately in the model, because often clinicians want to see that. Whether or not they should see that is a whole other issue.
That's a very good point you're making.
Right. So I guess I'm trying to get around this whole kind of black box.
Well,
right, and because then it's replicable, right? Because let's say I can use that model with those covariates, and there's a regression equation that may accompany it. Perhaps not with extreme gradient boosting, but let's say with Lasso regression or something.
Sure.
And I can share that model with somebody else, and they can replicate that perhaps in their data set and see does it predict outcome of interest, right?
Right. It's still. I mean,
is it black box?
Lasso isn't so black boxy, because Lasso is really a linear regression,
right?
Because
right.
it's just a special case of linear regression. Random forest is much more like a black box, and it provides a certain kind of variable importance, as you're noting. You don't just get back the prediction; you get back some list of the most important variables. But it does it in a way where it's not a coefficients reading, off the thing. It can't look at the model itself and figure out what the importance is. It essentially is equivalent to, it removes the variable and redoes the prediction and compares the fit. So it's a type of variable importance right there that doesn't rely on the model. You can do that exact same variable importance in any model, right? I'm not saying that there's not things available for algorithms. I mean, Lasso, you just look at the coefficients, much like regression.
Right.
And when we get to the machine learning, we'll talk about pitfalls of maybe doing that in Lasso. But I mean, it's still available and often used for high-dimensional data to get that. So, So I mean, I think when I say black box, it just means that there's no way to sort of interpret the relationship of variables.
Right.
Except as a whole in the outcome,
right.
Until you do something else to try to figure out, I essentially like comparing fitted procedures when I have a variable in and out and seeing the change in the R squared, right? That's essentially like
because sometimes I feel like you provide that initial table and people see those variables, and then sometimes they may be variables that are conceptually measuring the same parameter.
Right.
Right. And then people misinterpret those tables because they think of it in a kind of very traditional kind of
exactly
clinical epi framework.
Right. I mean, those kind of variable importance measures are also, they don't give you direction. They just give you, you can't say, well, when this increases, the mean goes up. It just says, I mean, you could do something else. Again, you always have to do something else besides just the fit and looking at the fit. And that's all I'm getting at. But on that note, causal inference really provides parameters that can be used as variable importance. That's exactly what we're going to talk about today. So you can fit large scale things, and then you can try to tease out what is the impact of each variable in this model using some of these parameters in causal inference as motivation. But it really is a form of variable importance. So this distinction between estimating a causal effect and variable importance is a question of whether you're assuming you're willing to make the assumptions that are necessary to assume a causal effect versus I'm not willing to do that, but I'm just going to use that parameter to measure the relative importance of these and get a direction as well. So the causal inference adds a whole other layer of assumptions and they're not, the important point is they're not testable by data typically. These are assumptions that you have to come in a priori to specify, usually orderings of variables, what happens first, what happens next. And so there's a set of assumptions that you hope you can justify, but you can't use the data to test in causal inference. They have to be stated a priori, and then you can say, given those assumptions, can I make some inferences about a cause and effect? And that's really an important distinction, of course. So again, this is the roadmap again. It gives you some notation to give you an idea. We're going to go over this in detail, but you specify a question, a causal model, and you specify, this right here would be like a causal model. It just says W comes before A comes before Y, right? And I typically, if I just write this, I'm always assuming that variables in the past have effect on every variable in the future. Now, there's exceptions to that we'll talk about, but that's generally the assumption. Now, if I have longitudinal data, these are assumptions are pretty good because I measure things at one time and I measure them another time, and that time ordering is given. But even in longitudinal data, you'll have a bunch of things measured at the same time, and you typically, if I want to disentangle the impact of a certain treatment, I have to make an assumptions about whether it comes before or after the other variables measured at the time. So it's rarely as trivial as just the time ordering. We usually have to add other kinds of assumptions. And then you specify the causal quantity of interest. We're going to go over what this means here, but you can think of these outcomes as counterfactuals. That's what they're called. So YTX means it's the outcome had everyone be given treatment, or that particular person's given treatment. Y not treatment is the outcome under not treatment. If I could do that experiment, all I would have to do is take the mean difference and I get the causal effect, right? It's a very empirically derived notion of causality. It's based on interventions, right? It's not, there's not subtler, it's not very subtle, right? It's just like I have a system, I change the system, and I look how the outcome changes. Right? So this is the thing we'd like to estimate typically, or some kind of parameter that's related to these counterfactuals. And what we are going to talk about in this course is how, or this day, is how we go from this thing here to this thing on the right. The one on the left is something I can't measure. I don't see, not everybody in my data set has treatment, for instance. Now, if it's randomized, I can just treat those people with treatment like the whole population. So that works out okay. But if it's non-randomized, I can't make that assumption. And the right-hand side is a function of the actual data journey distribution. This right here is just a mean of Y given A and W. So I can do a regression, right, of the outcome versus treatment and the covariates. And then the outer expectation is just taking the average across all the people, right? So the one on the right is something I could identify with data. The one on the left is the quantity I'd like to get. Causal inference is all about that equal sign. How do you assert that? So once I do that, of course, and I have a data structure, and importantly, I have some model. So here's my data. It's distributed according to P0. It just means it's some symbol for the true distribution that's unspecified, and then I'll fit this within a class of models. And again, we emphasize semi-parametric, so M is like a huge space of different models. It can include simple linear, it can include things with splines, it includes things like trees, anything you can imagine that has some smoothness in it. Once I do that, I can estimate the chosen parameter. Well, I'm just plugging in estimates for these things here, right? I estimate the regression, I plug in treatment for everybody here, I take the average, and I do the same thing, I take the same prediction model, and now I shift everybody's to not treatment, regardless of what they got, take the average of that, and I take the difference, right? So it's like that's an example of a substitution estimator, and then I interpret results and get inferences. So causal inference is just on this part here. Once we get to this part, it's just a statistical problem. We don't have to talk about causal inference anymore. So you can think of it as a very segmented kind of reasoning. You have the procedures and assumptions necessary to get identification of a causal parameter from to a statistical parameter. This is sometimes called an estiman. It's a parameter, it's a function of the data during distribution. And at that point, it's a math problem. How do I estimate that in an optimal way? Once I get that, I assert that, that equality. I wonder, I must have copied every slide twice. Anyway. So here's an example. This is an example out of my own research. I work a lot in acute trauma, in the trauma unit, trying to predict and understand the impacts of various variables on outcomes like death, which is a relatively, unfortunately, common outcome, or things like what they call hemostasis, which is getting your bleeding under control, right? So, and one of the factors that is a subject of research is what is the blood product ratio. You know, your blood used to be whole blood. They take whole blood and give back whole blood, but that's very inefficient in terms of storage and things like that. So they spin off the different products. You've got your plasma and your red blood cells, et cetera, platelets. And then they reconstitute it. And the question is, well, what's a good ratio of those things to get the best outcome? And it's a matter of debate, not totally clear whether it's always the same for everybody or what even ratio is an average best. So you could ask the question, what ratio would I give to get the lowest possible mortality? That's kind of a causal question. And then a more specific, a more refined causal question is not what ratio I would give to everybody, but how I would alter those ratios by individual characteristics to get the best outcome for that person. So this is sort of the cutting edge of causal inference type questions. It's called optimal treatment. And that's really part and parcel of precision medicine. That's what precision medicine is all about. Is can you derive a rule that you apply to your population that gives you the best possible outcome for all patients, right? So, causal model, it's a way to represent the background knowledge, and there's a couple ways to do it, and we'll talk about both. There's what are called structural equation models, or structural causal models. And there's graphs, and they're interchangeable. In many ways, they're interchangeable. There's some technical differences here and there, but for purposes of this course, they're interchangeable. Whether I define a structural causal model, which is an equation that tells you how every node variable relates to the nodes in the history, and the graph is sometimes called a directed acyclic graph because it can't have cycles. We're assuming if we have cycles are just in a graph are just a function of a lack of resolution, right? If you have enough resolution, you can always have a before and after, before and after, before and after. We'll first talk about structural causal models, and then we'll talk about graphs. But as I said, Structural causal models in some ways are easier because there's a correspondence to the methods we'll use. So when you write things down in terms of structural causal model, it's kind of easier to see how you might estimate these parameters. What's the motivation? Well, they're just explicit representation of your knowledge about the process, right? I mean, they don't require writing down a specific equation, like a specific functional form of how, let's say, mortality is related to patient characteristics and treatment. They're studied more in the abstract form, but they encompass everything you know about the process. This comes first, and this comes after, and this thing that comes after is a function of this variable and that variable, et cetera. You write them down all explicitly. They're also very useful because they can use them to define the causal question. We're trying to, causal inference is all about estimating the impact of intervention. So I can now intervene on the structural causal model, say, oh, I'm going to change this variable to some other value and keep everything else the same, and the structural causal model translates that into a specific new variable, which is called a counterfactual. And also, they can be used to whether the data assumptions are sufficient to answer those questions. This is is identifiability. I mean, for instance, I'll jump in a little ahead. If I have A and Y is my model, and then I have U, so unmeasured, and these are unmeasured, so I put a circle, and these are, sometimes I use a box for things. I can not identify the effect of A on Y anymore because it's confounded by this thing I didn't measure, right? So in this causal model, the treatment effect of A on Y would be non-identifiable, right? Because I have essentially unmeasured confounding. That's a simple example, and there's other more complex examples, but this is probably the most common form of non-identifiability is you have unmeasured things. You have them as part of your causal model because you think they exist and they have an impact, but you don't measure them, right? And so in your causal model, you want to represent both variables that you measure, but also variables that if they have an impact on the outcome, that you don't measure. And the combination of those and how they relate to one another will tell you whether I can identify certain pathways. You can think of this as a pathway right there. So there are both exogenous and endogenous variables. This is, older language, predates causal inference, although it's related. Endogenous means they're variables that are caused by other variables in the system, that they have an impact. Your exogenous variables are variables that nothing impacts. They're just standalone, right? And so usually those are things like error terms or things like that. So endogenous variables are the variables that we measure, essentially, the x's, or the A and the W and the Y. So you have some scientific knowledge about these things. We may have a time ordering, which helps us order them, and if we don't, then we have to put two-way arrows. We don't know which way the arrow goes. It should include all the variables that you measure or are considering measuring, and it could include things that you don't measure, which are called latent variables, right? So your whole system, endogenous variables, it could be complicated. It could have things that you measure, things that you don't measure. It could be structured by time ordering or a priori knowledge, somehow that you know that this comes first and the treatment comes after. Exogenous variables are like unmeasured errors. So there's just those things, and that's really because our systems are never deterministic. If we know a certain set of variables, I can't tell you what the outcome is going to be for sure. There's always uncertainty. I mean, unless you have a system that's deterministic, and that means statistics is not necessary anymore, because if I know this and that, I know the outcome. But in this case, since we have variation around a prediction, one way to characterize that is by introducing these idea of unmeasured errors. And so we'll also have, in that structural causal model, we'll have a system of unmeasured variables as well. They're not affected by other factors in the model, although they can relate. You can have them relate to each other. You can have U1, you can have an arrow to U2, for instance. We denote the distribution of all these by PU. It's just the joint distribution of all the errors terms. It's not going to be that important, but just for notation purposes. Now, here's where everything reaches, everything comes together, is that finally we have functions. So we have endogenous variables, we have exogenous variables, and then we have functions that relate them to each other. Now, because we're doing estimation in a very big model where we don't really have information on the functional form of these, they're going to be unspecified functions that we're going to learn from the data, right? So we're just going to call them fx or f, and we have the inputs inside them, but we don't really know what the function is. We don't know if it's beta 0 plus beta 1 x1 plus beta 2 x2, right? This is what if you're in that kind of system, that's a classic structural equation model system where you relate each of these, you can put a functional form in each of these f's, but that's not realistic for public health since we typically don't know the functional form. So this is the way we specify them. So xj, that's the variable, will be a function, fxj, so it's not, you don't have the same function for every variable. Every variable gets its own function. And it's a function of both the parents, so that means every variable that's in the past of xj or has an arrow into xj, and some random error exogenous variable u xj. So I mean, for instance, I could have xj minus 1 and xj minus 2, both going to xj, right, here. And then there may be an xj minus 3 that does not go to xj, but goes to maybe xj plus 1, and then this goes there. That would be an example. So then fxj of, well, the parents, what are the parents of xj? That's a parent, and that's a parent. It's those things that have an arrow into the node. So, right, it would be a function of xj minus 1 and xj minus 2. And then implied is there's a uj, xj, going into it. Again, it could be something like this. I mean, this would just be an example. It could be this thing is equal, for instance, to beta 0 plus beta 1, xj minus 1. Plus beta 2, xj minus 2, plus u xj, right? That would be a specific functional form, but we're not going to assume that typically. We're going to have to learn these using machine learning, the ones we care about. Now, typically the default is that anything that occurs before a variable gets included as a parent. You can, unless you have specific knowledge that says, oh, this variable comes before, but there is no arrow from this variable into that variable. That's called an exclusion restriction. It just means it's a variable in the past that you don't think affects this particular variable. And again, becomes very important in causal inference course when you talk about things like instrumental variables and other kinds of more complex situations. For us, it's not going to be terribly important.
Prior slide. So for your prior example, when you're talking about sort of trauma, right? Would
Right.
you be looking at like each of those as like a hemoglobin or like a blood count, for example, as your like prior X sub J's, or are you thinking of it as like different variables that are then feeding into the model?
No, I mean, it could be the same variable measured two different times, right? But so the answer is it could be both.
Okay.
But I was thinking in this case, it's like two different things that come before n. Because generally, if you have longitudinal data, you'll have things like, you'll have, I'll make L sub 0 goes to A sub 1, goes to L sub 1, goes to A sub 2, that there's a time ordering there, and you give them different symbols to keep the time ordering separate, and ultimately goes to LK, which is equal to the outcome. So you have a whole sequence of things measured over time. Yeah. But they could be, there's no difference in how you use the variables, whether they're a different name or not. It's just a variable that comes in the past. Yeah. And it's a good question. When we get into situations like this, I have to decide, do I, when I'm trying to predict, let's say LK, do I use the recent past? Do I use the entire past? And sometimes you will impose exclusion restrictions because you just think, well, let's say LK is heart disease and I have cholesterol the previous time. It probably, cholesterol, 5, 10 measures ago probably has no impact beyond the more recent one, that any pathways go through that. And it's makes sense to exclude that from the structural causal model in terms of variables that influence LK. But these are kind of assumptions made for convenience purposes. If you have enough data, you don't need to make them, and you just conclude it. If you have a finite amount of data, you can't fit huge models, then you start doing this for necessity, not so much because you believe it, because there probably could be some small effect, right?
Just a question about
Sure.
the X sub J.
So these are deterministic functions. They're functions of random error that you don't measure, so they don't look deterministic. But in theory, once I knew the u and the x, and I knew the f, then I put different inputs in, and it's going to give me a different number there, right? So the way you generate this distribution, like if you're going to simulate data from these kind of models, you first simulate a u. You draw from some random multivariate distribution, like a random normal or something. So I generate all my u's first, and then I generate my x's based on these x's. So if I do them in the sequence they come. So if it is ordered like this, x2, x3, and I have a u1, u2, u3, and these could be related. Then I first simulate my u's. The x1 is just a function of u. Oops. So x1 would be f x1 u1. And I'll actually put it. x2 would equal f x2. Well, it's x1 goes into it here. So x1, and then u2, and x3 would be f x3, x1, x2, u3. So that's how the graph corresponds to the list of models. Now again, you don't have to estimate each one of these functions in order to estimate certain parameters. Sometimes it doesn't matter what fx1 is, it doesn't impact a particular parameter of interest. But typically the last one, which is going to be your outcome typically, that is a function of the past, and that's a function that you need to estimate. So again, if I was simulating, I could take u. Actually, this is not a bad idea to just give some intuition. I'll use R. So I could have u1 is R norm. Let's say sample size 100, and 0, 1, and I'll just have them independent. U2, R norm.
He's sleeping, I think.
Oh crap.
Yep.
Okay, good. Zero, 1, U3, R norm, 100, 0. Then X1, I could just make that equal to U1. X2 might be beta 0 plus beta 1, X1 plus U2, and X3, beta 0 plus beta. Okay, I'll put beta star because they're different coefficients. Star 1, X1 plus beta 2 star, X2 plus U3. That would be an example how I could simulate. I could simulate first the 3 error terms. Each of them is a vector of 100. Then I just call U1, X1, U1. I don't, I could do something else, but it could be 10 times U1, whatever. X2 would be, I can make a linear model of X1 and X3, a linear model of X1 and X2. Both of them, you add an additional error term. And that's how I could simulate data that would come from that causal model.
So, is there a particular reason why in your simulation you could use any function other than the normal, right?
Yeah, yeah, any function. Yeah, it doesn't specify. I mean, I'm not specifying that. I'm just doing what's convenient.
Yeah.
But yeah, no. And the whole idea of that these things we're operating a non-parametric or semi-parametric model, so we are not assuming we know anything about the distributions, and we let the data tell us what it is. But if you're simulating, of course, you have to know. So, and a good way to understand any of these concepts is really simulation. How would you simulate data, and how would I simulate the estimator? It's always a good way to sort of frame them, particularly with causal inference. Because if I give you a causal model and I say, give me code that simulates data from this model, if you can do so, that means you understand it. And if you can't do so, you don't understand it. It's pretty straightforward. Just as talking about HIV kind of studies. So it's just really, the thing that causal inference does is you're really taking it seriously. It means that you can't just get a spreadsheet. And that's true of the kind of methods I'm teaching in general. You have to have very detailed conversations with the researchers who understand the relationship of variables, because you gain a lot by knowing what variables in fact other variables. And if you can exclude some of the arrows, that can actually help you quite a bit to identify your effective interest. And so, and the other thing you can do is you can say, if this is your causal model, how would you define an intervention that would give you back the causal effect of interest to you? I always start conversations with my fellow researchers in that way, like what is the intervention you would do that would define a causal effect for you? And that leads to a particular parameter if you do that. And it gets them also to think carefully about how to translate their conceptual systems problem into a specific targeted statistical problem. And this is just an example of that. Okay. Does the use of platelets decrease mortality? That's the question. So you can give platelets or not give platelets. That's it's often a decision made by the surgeon and depends on the bleeding status of the patient, whether their bleeding is controlled or not. So we'll call A an indicator of platelets, no being 0, 1 being yes. W represents a whole vector of things that you might measure. Like you get things like there's all these biomarkers of the blood, INR and thrombosin or whatever it's called. All these things that measure clotting and other factors related to clotting, as well as how injured the patient is. What type of injury, blunt force versus let's say a head injury, TBI. TBIs can have an impact independently on coagulation and by unknown mechanism, but they know it occurs. And then we'll call Y an indicator of death within 6 hours. So this implies that my model, causal model, is like W goes to A, goes to Y, right? And I'm interested in the impact of intervening on an A. So I want to set, for instance, if I set A is equal to 0, then I have W 0, Y. But there's no longer any arrow from W to 0 if I set everyone to 0, because I've precluded them having an impact, and then I could have W1, Y. Again, I eliminated this arrow by intervening. So that may be a question, that may be a type of question they might say, well, I want to know what happened if everybody got platelets and compare that when no one gets platelets, and that difference in that mean of the outcome will be my definition of a causal effect.
Notation.
Yeah.
So would you, to differentiate the
Yeah.
Y's, why not, why not?
Right, so this would be, I'm going a little bit ahead, but that's okay since it's my fault. Won't work. Okay. So this one right here is like saying, well, I want a new structural, which is F. So it would be Y. It would be Fy W0 UI, and this one would be Fy W1 UI. So what I would do is if I, in theory, damn it. Oh, there we go. Good. In theory, if I knew these Fy functions, I would put in the W that I observed for that patient, make their treatment no platelets, take their outcome Y, and that would define my outcome. I mean their error term Y, and that would define Y0. And then I go back to that same equation, change the 0 to a 1, so everybody gets a 1, keep W the same, right? I'm not changing that, I'm just intervening on one node, and also keep the error the same, and I get Y1, and then I compare the difference, and that's the causal effect. So that's how you think about it.
So
Yeah.
in your previous,
And this is just putting it in, combining it in notation. So FW would be just a function of it's in essence, W is exogenous in my model. I don't have an arrow going in it from something else. I mean, there obviously is arrows into everything, right? The whole world is an interconnected nexus of arrows, but you make simplifying assumptions. If there's no arrows into W that are also into Y, then you just don't have arrows there. So in our system, effectively, W is exogenous, meaning nothing's causing it. Then I have treatment A and outcome Y. Errors are just routinely, you just generate an arrow for each node. And then W is just a function of the error. A is a function of W and the unique error for A. And Y is a function of WA and the unique error for Y. So if I was going to simulate this, as I said earlier, I'd draw you from some distribution. Could be multivariate normal, could be multivariate logistic. I don't know what it is, but something. And then W is defined at that point, right? Because it's just a function of W, UW. So if I know that function FW, then I know deterministically the W's for every person. Then I can generate an A by taking these inputs here and applying that function, whatever it is. And finally, I get the Y, right? So this is how you would do it sequentially if I'm generating data from this underlying model over here. It's just like I talked about earlier, it's how you simulate data from that system. So I've already gone over this, but structural equations, these are called non-parametric structural equation models. You might have heard of SEMs, which are used often in psychology and other fields, and there are ways of doing pathway analysis and things like this. And so this is related. It's related very closely, just that the Fs that we have, we're not specifying what they are. We have to learn them from the data, right? So we don't typically have something like this where a node is a linear model. We don't assume that. We let the data speak for itself. However, if you have information about the functional form, you can use it. I mean, it's very rare, and I would say the only time Where I've seen it practically used is if I know a variable has a specific range. So I know, let's say, an outcome can only be between, I mentioned this yesterday, like body weight. Can't be negative infinity and positive infinity, right? It can only be a specific range, and you can impose that in how you model it. There's a way to impose ranges on variables. That's the most likely. And the other things are conditional independences, or exclusion restrictions, where I don't necessarily, let's say I can tell you that for sure A is not a function of blood pressure, I could take that term out, right? Now, those are the only two kind of restrictions that there's any typical knowledge or theory about in our field. Now, if you're in engineering, you may know it's an exponential function. Or in physics, they're well-defined functions. But in public health, we only use functions like linear or logistic models because they're convenient. We don't have theory to say the relationship will be that typically. And that by estimating these functions under a semi-parametric or non-parametric model, you're really respecting what you know about the data. So one consequence of these methods is that often your confidence intervals will get bigger because they reflect the actual information you have. Like you can get an artificial confidence interval small by assuming a linear model, and it's going to estimate that. I'm going to estimate that and assume the linear model is true to get your confidence interval. You might still fit a linear model as an approximation, but your confidence interval is going to be bigger because it assumes that the true underlying model can be anything, and you're just fitting a linear approximation to it. So you get more accurate inferences this way. That's one way it cuts down on the false positives that are apparently epidemic in the literature, is that you really are getting inference for what you really know and not inference for knowledge that's really you don't know, you don't have. It's artificial knowledge. So two other kinds of assumptions that are built in. I already talked about exclusion restrictions. That just means there's an arrow in the past that doesn't go to a particular variable in the future, that you assume there's no independent pathway between two variables. And again, that can be effective knowledge. As I said earlier, if I know the most recent measurement of some biomarker, the outcome will be independent of a biomarker earlier if I know the one that's more recent, right? So if I have my latest cholesterol measurement, for instance, then the outcome could be conceivably independent of my cholesterol measurement 5 years ago, given the one I just took, right? It looks like this, right? X1, X2, X3, and I'll make an outcome Y. And I might have this, but I don't have any arrow. I don't have this arrow, and that's an exclusion restriction. That means I'm assuming that X2 has no independent contribution on Y beyond impacting X2 and X3, which impact Y, right? So, oops. An interesting case of exclusion restriction is instrumental variables, where I have something like, I have something similar. I have R, and then I have an A, and I have a Y, and then I might have unmeasured things. It turns out you can derive causal estimates of the effect of A on Y, even though I have unmeasured confounding here, if I have this variable here, which is an instrumental variable. Which is an instrumental variable because it has the exclusion restrictions. It goes into A, but it doesn't go anywhere else. So anybody can give an example of an instrumental variable? Something that impacts your treatment, but doesn't have any independent impact on the outcome?
We typically use a facility as an instrument.
Yeah, that's a good one. Yeah. So sometimes a facility might impact whether or not you get the treatment, but it shouldn't have any impact on the outcome. One of the obvious ones is treatment assignment in a study. If you have people that don't always take their treatment, they have noncompliance, and you assume that treatment assignment itself could have no impact on your health except through whether or not you take treatment, then that can be used as an instrumental variable, and then you can get an effect of the drug even though you have missingness that's informative, right? So And that's a lot of literature about instrumental variables in public health has to do with noncompliance and things like that. So it can be used there too. Again, I'm not going to go over those kind of estimators. They're somewhat specialized, but yeah, there's lots of interesting things you can do with causal inference. You know, lots of situations where you can understand Bergson's bias in causal inference. You can understand missingness by doing these kind of structural equation models, et cetera. They can elucidate things that are harder to explain without it. So it can be very useful in that sense. And also, it can help you to understand more complex parameters like mediation, right? Because you can have, I might be interested in the impact through an intermediate variable versus not through an intermediate variable. And dealing with these structural equation models can help you refine how you define that mediation. So, I mean, the sort of underlying goal of using this stuff is that you really try to restrict your assumptions to those things that you can really support. And it, as I said, it often means collaborating closely with your researchers to make sure the assumptions are well supported. Oftentimes, that's not enough. Like, I mean, in an observational study, there's still things like unmeasured confounding, right? You can't assert that you've measured every compounder. So you sometimes say, well, I'm going to get the estimate under the model of no unmeasured confounding, even though I'm pretty sure that doesn't exist. I think it's as close as I can possibly get. So you do have to make assumptions by convenience if you're in a situation of observational studies, typically anyway, right? We don't have the world fully elaborated and every variable measured that could impact an outcome and also impact intervention or treatment of interest. So it's just unavoidable, but at least now you're going to estimate things without making any further statistical assumptions, and you'll get maybe the best estimate you can given the limitations of the data. So causal graphs, I've already kind of alluded to this. It's just another way to represent the structural equation models, and you can do it explicitly in a graph. So I can write a series of, F's that correspond to this graph here, right? Let's do it. Oh, actually do it. So what's W a function of? Just UW, right? So I have FW, UW. What's A a function of? Well, it's a function of W and UA. So I'm just getting the standard graph W, UA. And then finally, Y is a function of A, W, and U. Oops. So now the graph gives you some more information than just the structural equation models, because it also can tell you if the errors are related. I have to say this is an esoteric part of causal inference where you try to identify things where certain error terms are related and some aren't related. And it's a little bit, since they're always exogenous and unmeasured by definition, you rarely have any information on it. So it's kind of a silly esoteric exercise, generally speaking, but that's the additional information you get from a graph that isn't directly come from these three equations. Later? No. Okay, so once I have a graph, and we've already talked a little bit about this, like I've talked about interventions on a graph or interventions on a structural equation model. Now we have to define our causal quantity of interest. This is something that we believe will address whatever the scientific question is as closely as possible. So what theoretical intervention would you do on the system to test whether or not some variable has an impact on another variable? So again, this stuff is only interesting in systems and data generating systems that aren't equal to the experiment of interest. If it is equal to the experiment of interest, if I turn a knob and I get a measurement, and then I can turn the knob more and get a different measurement, I don't need this fancy stuff. I just compare the measurements when I turn the knob, right? So that's why, many things like engineering and things like this, where these are controlled experiments and essentially infinite in sample size, you can keep on doing them. they have much different approaches than we do. We're trying to really put a lot of effort in understanding the system and characterizing it because we get one shot, right? We can't go back and say, well, let's tweak that dose and we don't have irreplaceable, we don't have replaceable units and things like that. So, and we also need to make inferences when you're dealing with things like, airplanes and you're designing them. You don't really need to make statistical inferences because you can just do repeated experiments over and over again and test your engineering assumptions directly by wind tunnel, whatever. So public health is different in these fields. So and I think that's underappreciated. A lot of big data stuff has been translated from things like engineering and other fields into public health, and they come without inference. And for us, inference is really important because we don't get the luxury of having an infinite number of experiments we can do. We just get one, and we have to make some inferences about it, which means we have to predict what the sampling distribution would be. We don't get to see it directly. Obviously, the first question is, which variable do you want to intervene in? It may not be just one. I can have situations where I'm interested in the joint intervention. I want to know if this dose of this drug goes up and this dose of this drug goes down simultaneously, what happens to the outcome, right? So it doesn't have to be indexed by a single intervention on the graph. It could be you're intervening on two nodes. That's certainly possible. And when you talk about longitudinal data, it is often of interest. I want to know where the whole treatment pattern would be and how that would affect an outcome. So in that sense, the number of interventions of interest are really the number of time periods that I'm looking at in my data. And I'm looking at the joint impact of all of them. Now, there is this kind of debate in causal inference literature, which is if you have a characteristic that can't be intervened in, we shouldn't make causal estimates. Because I think that is taking it a little too seriously. I don't agree, but there are kind of variables like gender and things like that. There, you can talk about a causal effect, but you can never have an intervention which actually does it, at least practically in humans. So, we're going to ignore that. So when we talk about interventions, they're really theoretical interventions, and it may be possible and may not be possible to do in actuality. Obviously, it's more compelling if the intervention is possible. We're talking about a drug treatment. It's possible to have a different dose or to have a different treatment. Other things like ethnicity, socioeconomic status, can be varied, but it's difficult, things like that. You can talk about counterfactuals, but the experiment is hard to envision that actually makes that the case. We're going to focus on one variable at a time. We're not going to focus on a longitudinal case. Longitudinal cases, that's relatively straightforward extrapolation of what you learned about a single point intervention. As I said, it's just intervening on not one node, but several nodes at one time. And if you haven't noticed, we typically use A for the intervention. So I call the variable A if I'm interested in the effect of it, essentially. The next step is what kind of intervention you want. One kind of intervention is to set everybody at the same level in the population and see how that changes the mean. Another one could be to set it according to a rule. Say, I could have dW equal the indicator that W is greater than some constant, delta. And I would look at, in this case, I'd have Fy, it would be W, dW, and Uy would be the outcome of interest. And so that's called a dynamic treatment. You're not looking at a uniform treatment across the population, but a uniform rule applied. Everybody over 200 cholesterol gets some Lipitor or whatever it is. So something like that. You don't give it every, and these are often very practical because you don't, oftentimes in the data, there's no experimentation for certain people. You don't get people who have extremely low cholesterol getting cholesterol drugs, right? So it makes no sense to give them, assume they're going to all get a cholesterol drug and see what the mean would be. You have no information in the data from it because people like that never got a cholesterol drug. So that's called a positivity violation, which is an extremely important concept in causal inference. And these kind of dynamic treatments can sort of address those kind of situations where there are subgroups for which you only get one treatment ever. You don't get the alternative. And you still want to include them in the estimation of the mean. You can have other stochastic treatments, which are, I give you a treatment, but it's a coin flip, right? That's a stochastic treatment. And I'm going to get, now my FY is going to have a random variable here. So anyway, these are all different types of outcomes. And then you specify an outcome, whatever particular disease status or whatever outcome you're interested in. So in this question, the use of platelets reduce the risk of death by coagulopathy. What is the intervention variable? Platelets. What are the interventions of interest? I don't really say, but what might they be? Yeah, I could compare the mean when everybody got platelets to the current mean where only some people get platelets, for instance. So that's an example of it would be like EY1 minus EY. So the mean of the outcome under uniform intervention compared to just the current outcome. You could see how much would it change if everybody got an intervention. That's one way. Or it could be EY1 minus EY0. That is the outcome when everybody gets platelets versus nobody gets platelets. And then, of course, the outcome in this case is death. So that would be how you would translate that into this kind of system, into a parameter. And that I've been alluding this the whole time. Counterfactuals, those are those outcomes under different interventions that you didn't observe in your data, but you want to speculate about what the mean of them would be under uniform interventions, for instance. So they're called counterfactuals because you want to know the outcome counter to fact an individual got a certain treatment they may not have gotten. That's why they're called counterfactuals. They're also, better name really is potential outcomes. They're just the outcomes under different interventions on the graph or in the structural equation models. And as I said, we showed they can be derived from structural causal models. You just plug in the intervention you're going to have where A goes, and that outcome is now defined. The counterfactual outcome is then defined. So here's an example, a simple example. So I just have an A and a Y, there's no W. And so A is FA-UA, it's like randomized, and Y is just a function of A. If A is 1, well, I've taken the arrows out, right? So these arrows are gone. Since if I intervene, make everybody 1, nothing can impact it anymore. I've set it. I've turned the knob, which affects A, which is 1, which affects Y, right? So it's just and this should be read Y sub 1. That would be the counterfactual outcome if in this system I made everybody's A a 1. And this is just doing it again. So baseline risk factors, platelets, hemostasis, or death. I got my error terms. Again, we generally aren't going to estimate these anyway. So we just assume that they're come from some unspecified distribution. Now, when I have counterfactuals, I can define a so-called full data structure. Think of the full data structure as the data set I would have had had I been able to intervene in the way I want to estimate the impact of. So if I could intervene, I could get, for individual, I could get W, of course, I could get Y1, and I could get Y0. And that would be XF. So full data would make it very easy to estimate the causal effect. It turns out you just take an average of the difference, right? So my causal effect, let's say ATE, would be the mean or the average of yi1 minus yi0, right? It would be trivial. I would just simply take the two, take the difference, and take the average, and that gives me a direct estimate, okay? The reason that this is useful is because it turns out you can treat causal inference as a missing data problem. It's just, and A becomes, so the observed data, is WAY, and A really is the missingness indicator. It tells you which of the Y's you get, right? So you can think of, I'm missing, if A is 1, I'm missing the counterfactual A is 0, and if A is 0, I'm missing the counterfactual A is 1. And you can apply missing data techniques exactly under that scenario. Things like inverse weighting, IPTW, and imputation, which is like G-computation or substitution estimators. They're both just classic missing data problems, but applied to this data structure where you assume that you're always missing one outcome. And a lot of the theory that around these estimators came from treating the data as a missing data problem, because that is a well understood aspect of statistics. So one of the most common parameters in probably 90% of estimates of causal impacts are average treatment effect, as when the treatment of interest has two levels, let's say 0 or 1. It's arbitrary, but we can always characterize one as 1 and one as 0. And you're interested in the difference of that. I mean, you can have, again, it doesn't have to be additive scale. It doesn't have to be a difference. It could be, you could have EY1 over EY0. That's causal relative risk, right? Causal relative risk. You could have causal odds ratio, which would be EY1 times 1 minus EY0 over EY0 times 1 minus EY1. Anyway, it's just two numbers. You have two counterfactuals, you have the mean of them, and you can relate the mean different ways. And average treatment effect is the most common way it's done. But all these things, if you can estimate the average treatment effect, you can estimate the causal relative risk, you can estimate the causal odds ratio as well. There's one more parameter that's often done. This is for treatments that have more than two levels. So let's say you have an ordered treatment that goes 0, 1, 2, 3, 4, for instance. There's these things called marginal structural models. Marginal structural models is a term that's used constantly. It's used to describe an estimator. It's not an estimator. It's just a parameter that you're after, and it just describes how the counterfactual mean changes when you change the intervention. So I think of it this way. I had a graph here, and I'll have little a, and then I'll have E, Y, little a. So I have 0, 1, 2, 3, 4, and I can plot what these would be. I could report each of these separately, each of these 5 numbers, or I could fit a line through them. The marginal structural model is just fitting a line. It just gives you a, beta 1. But it's you're essentially estimating the same thing. Now, a more subtle way of looking at it is not that the truth is it's a line, but you're estimating a projection of a line on the truth, and that's what this is here. But that's probably more realistic. One of the papers that originally was published, kind of demonstrating the use of marginal structural models, generated data from something where the marginal structural model, the true one, was not a line. And that's because it's very hard to simulate something where the marginal structural model will have a linear if you're in a nonlinear model, that it'll have a linear component. This is basically what you're mainly doing. However, to conceptually, to think about it, you can just think about it as the line that goes through these points. And you get the slope, you get the intercept, and you can now reconstruct the counterfactual differences of any difference. Like if I want to know the difference between 2 levels, that's 2 times beta 1. 3 levels, 3 times beta 1. Oh, again, I mentioned this. So why we can think of this, the observed data that we actually observe, we just observe a single A and the Y based on that A and W, and how we can link that to structural equation models and a missing data problem is you think of this as the full data. This is some function of the full data and A, and this is the specific function, right? So I get A and I get W, and I either get Y1 or I get Y0. This should be Y0. In other words, that's the mechanism by which you could think of this as a missing data problem. You can think of everybody having in them their 2 counterfactuals and their W, and then your process of grabbing them only gives you one of them, depending on which A that you're assigned. And again, it's a useful thing to think about theoretically. It's not so useful in practice because it doesn't really change that much. Okay, I'm just going to do a couple more slides and we'll take a break. But I'll just get through this now. So the last thing to do is the statistical model. As we said, our statistical model is going to be semi or non-parametric. That's why we're going to use machine learning. If it was a linear model or a smaller parametric class of models, then we could estimate causal effects using these standard approaches, right? I mean, you can think of a coefficient in a linear model as a causal effect if the model's true and the same assumptions apply. But in our case, we're going to allow for any kind of functional form, which means that our effects are not going to be necessarily characterized by a coefficient in a regression model. And that's why we're going to talk about this next, machine learning methods and data adaptive, because if you're not going to assume a model, I have to have some way to estimate a relationship between a bunch of variables. I mean, W, in this case, the covariates can be a list of 1,000 long, got 1,000 things. And the trauma data set, it's at least hundreds of potential confounders. And so you actually need data adaptive procedures in order to realistically fit any model. And we're going to talk about ones that have some virtues over competitors. So here, this is something really to pay attention to from a practical standpoint, because it's a concept it's a concept obscured by standard traditional parametric forms. You can't detect this unless it's extreme. It's extreme form, it's called collinearity. But in non-extreme form, it's just a violation of positivity, and if you fit a logistic regression, it won't warn you. It just extrapolates through areas of the data where there isn't any experimentation. And here's what it means. The assumption is behind these estimators is that for every group defined by W, so you have a bunch of covariates, there is a positive probability of every level of treatment. So for every subject, they have a positive probability. They could have had A is 1 and A is 0. If there are subgroups for which the probability A is 0 goes to 0, that means I can't estimate the effect in that subgroup because I only have one outcome, right? The only way I can estimate the effect is to extrapolate, and that's what parametric models do. I'll give you a simple example, right? If I have I'll make this A and this Y. And this is W equals 0, and let's say I have W equals 1. I only have a point. There is no A, this is A0 and A1. There is no A1 when W equals 1. So if you fit a linear model, it's going to assume that's the case, right? It'll do it fine. It won't create an error or anything. It'll just extrapolate based on that. But in this case, if you look, this, you know what this thing is called right here? The probability to treatment given covariates? What is that thing called? Yeah, it's a propensity score. So it's the propensity score right here. And there, one important diagnostic to do for these methods is to look at the propensity scores that because you'll end up, we talk about targeted learning, part of doing that is estimating these propensity scores. We use them to augment our original fit because they really kind of capture all the latent confounding that's left. And if you have values of these that are very, very small, less than 0.05 or 0.03, it tells me I have a problem. Like I cannot estimate the impact over all the data because there are subgroups of the data that have extremely low probability of getting the other treatment, and therefore they don't have enough experimentation. And this is a chronic problem in observational data. In most situations, I would say I encounter some positivity, that you just find people for which they always got one treatment, and therefore you can't, in a non-parametric way, estimate the impact of treatment when you only have one value there, like that. So again, I alluded to this. In observational studies, there's always unmeasured confounding, meaning technically our assumptions that we need to derive our causal effects are not true. You know, again, we start with this, y1. So that's the mean of the outcome had if you got one. And I know some people didn't get one, so I can't estimate it. But then I can always do this. This is making no assumption. So I'm just now conditioning on W and then taking the average across W. But under this assumption of the causal of this model, you know, the model W, A, Y, that Y sub A is independent of A given W. That there's nothing that the treatment assignment gives you about the prognosis, about the outcome, once I condition on W. W has all the information. That treatment assignment no longer has any information about the outcome. That's the assumption of that model. That means I can write this as EW E given A is equal to 1 in W. Remember, I can add a conditioning statement if it's independent, doesn't affect it. And that just turns out to be EW E Y given A equals 1 in W. So that's the identification. We didn't go over a lot of, I didn't go over the details of identification. This is essentially the randomization assumption or the no unmeasured confounding. We generally don't know this is completely true, right? So what are our options? If we have observational data, well, we can get more background information or collect more variables. That's one thing to make sure we have all the confounders. We can give up, and sometimes that's the right thing to do. We simply don't have the information in the data, and people don't like to give up, but that's a reasonable option sometimes. Or we can just estimate the effect, assuming no unmeasured confounding, and see and get something that's at least reflective of possibly the causal effect, with the caveat that I can't be sure that I'm not measuring the impact of something else in the data I haven't measured. With these methods, the machine learning methods that we're going to talk about, at least you don't leave anything statistically on the table. You're going to adjust for aggressively as possible for the W, right? It's going to find the model that predicts Y the best from all those W's, whatever they may be. So it's going to get rid of as much confounding as possible. And if there's residual left, hopefully it'll be minimal. But you have to do something, and observational data is proven to be useful. So you might as well do what you can with it, just with important caveats and constraints. Is we want to figure out how to estimate this quantity. That you can see that most of our causal effects will be a function of this regression, the regression of Y on A and W, and we're going to concentrate on methods to estimate that prediction function, right? And we want to do it in a way that's justified by theory, that's, can capture patterns that are smooth or that are very rough, and can do so in an automated fashion. And so that'll be the topic of the next lecture. Okay, let's take about 20-minute break. Any questions? Okay, we're gonna take a break, and then we'll come back and I'll start talking about machine learning. It's gonna be kind of a drastic departure, and then we're gonna come back and merge the causal inference and the machine learning in the final lectures, okay, the final 2 lectures. But first of all, the first thing we have to figure out, if I go back here,